Okay, so this is section 8.3. I'll go ahead and just start reading. It says, in this lesson, we study of hypothesis tests. That's a strange language. Hypothesis tests about a population mean, which is mu, when the population standard deviation is known, which is not likely, but the tests are a little simpler, so we'll begin with those, and then we'll do a population standard deviation that's unknown. Okay, so first it says the mean IQ for the general population is 100 with a population standard deviation of 16. I think it's actually 15, but we'll go 16. Your professor believes the mean IQ is higher for college statistics students. Absolutely, I do. He gathers 35 random statistics students and observes a mean of 106. So that is a little higher than the average. But I'm talking about all college statistics students, not just these 35. So 106 is fine, but is that within the margin of error of the normal average? Well, we'll have to see. So we're going to test my claim that I think that the mean IQ is higher than 100 for my stats students. Okay. So again, now the main difference between this and the last lesson is we were doing proportions in 8.2. So the claim was that, the first one was less than 50% of people are going to vote for a candidate. That's a claim about a proportion. Okay, but here I'm making a claim about a mean. So when we talk about means, there's just different rules. Let me remind you how means work. So I'm going back into chapter 7, and this time I'm looking for 7.4. Where we had done a bunch of, we were rolling dice and computing the average roll. And in the simulation that we did, I think some 30-something rolls, we got sort of a bell-shaped distribution. And then we took it into the thousands, and we got a beautiful bell-shaped distribution when we did 1,000 trials of rolling 4 dice and computing the average. And so from that, we learned that averages have bell-shaped distribution, but technically the sample sizes need to be pretty big. More than 30 is the rule of thumb. So let me see if I can find the central limit theorem. Here it is. This is for means. Basically, a distribution of sample means right here is approximately normal if your sample size is bigger than 30. And it's okay if it's not bigger than 30, but then you'll have to kind of investigate the population that you're sampling from. That has to be normal if the sample means are going to be normal and your sample size is not bigger than 30. So we're going to be checking the criteria for normality, but it's different now. Now the sample size needs to be bigger than 30, or you have to be sampling from a normal population. And the mean of sample means is the mean of the population you're sampling from. And the standard error is sigma over the square root of n. I think I'll copy that because we're going to be using it. And let's go into our lesson. Okay, so it says very first step says to gather the data and the level of significance and check conditions for approximate normality. So you're going to need this x bar, which is the mean from the sample. And it says it's 106 from the sample. So x bar is 106. We'll need a population standard deviation. Well, for IQ scores, I think they scale them so the standard deviation is known. It's a long story, but standard deviation is 16. And that's a population standard deviation. Sigma. Remember, if you don't know sigma, it becomes a t distribution. The sample size was 35 students. Okay, and remember that what we have to check is either, either n has to be bigger than 30, or the population is normal that you're sampling from. Okay. So check that. Here we've got n is 35, which is bigger than 30, so we're okay on this. Any questions? Okay, so this just has different criteria. Now you have hypotheses. The null hypothesis is similar to before. It's probably easier to do the alternative hypothesis first. The only difference here is that you're testing a claim about a mean. Before it was about a proportion. So we said P equals 50% or P equals 20% on the two examples. Those are percentages, which are the same as proportions. Okay? This is means, and means are, a population mean is mu. So you can say that mu is less than some number. Mu is greater than some number. Or mu is not equal to some number. So that's the main difference so far, is it's a claim about mu, not p. And then the null hypothesis has to say that mu is equal to to that number. Okay, so I'll say the same number as below. Okay, so on this problem, you believe that the IQ is higher for college statistics students, higher than what? 100. Okay, which is everybody else. So again, normally I start with the alternative, that mu is higher than 100, and that's for all statistics students. Okay, the null hypothesis, you just change this to an equal, so mu equals 100, it has to be the same number. Okay, now you have to remember this also determines the tail for the test. This points to the right. So just as a reminder, this is going to be a right tail test. H1 decides the tail, because H1 is the thing you're trying to prove. Okay, any questions? Now the test statistic, I'll remind you, see, I'm going to do a little tweaking here. First of all, I'm going to paste in something that I'm going to erase. Remember that you're going to take a z-score, or you would take a z-score. No, you do, because we know the population standard deviation. So the z-score of a sample mean would be the sample mean minus the mean of sample means over the standard deviation or standard error of sample means. And based on the formulas I put down over on the right, the mean of the sample means is the mean of the population you're sampling from. And the standard error of sample means is the population standard deviation, which we're assuming is known, divided by the square root of the sample size. Okay, so you'll need that. Okay, and just moving things around a little bit. Okay, so I think we can do this computation. So the sample, oh, and maybe the note should be added. We get mu from the null hypothesis. Okay, so the sample mean was 106. We assume the population means 100. That's what it is for everyone else. So that's kind of a status quo assumption. Sigma was 16. And then you divide by the square root of n, which is 35. Now, there are no decimals anywhere in what I wrote down, so I won't be too surprised if evaluating this gives a number that doesn't have a decimal. So it usually gives decimal answers when you ask decimal questions. If there's no decimal, it's going to try and simplify as an exact expression. So just a real quick, let me just show you what I mean by that. I'm having trouble. There we go. Focusing, trying to focus. There we go. All right, so it was the 106 for the sample mean minus the assumed population mean of 100. How many standard are the apart? Well, I think the standard deviation was 16. Divided by the square root of the sample size, which was, I think, 35. If I hit enter, it does simplify it, but doesn't evaluate it. And so these calculators that do simplification like this, you have to hit the approximate equal key, which is down right above the enter key here. Make sure you just tap the approximate equal if it does that. And so you get a 2 point, I'll say 2.22. Okay. Any questions? Okay. And then you need a critical value to decide if this is statistically significant. This was a right tail test. Okay, so remember our H1 said that the mean is bigger than 100. So that makes it a right tail test. Okay, and so we'll draw a distribution here. Label it Z. And Z is centered at 0, and our test statistic was 2.22. So we'll mark that off here. Oh, no, I'm sorry, this is the critical value, my bad. So we're trying to do the critical value. And that depends on the level of significance. And I don't know what that is. So let's go back here. The weirdest thing, it says 4% significance. I don't get that. But maybe I'll mark it down here. Alpha was 0.04. So it's sort of a strange number on that. But we're going to go with it. So with 4% significance, we're supposed to look this up on table A2, bottom row. I'm going to grab that and erase what I did before. Okay, 4%, and it's a one-tail test. So 0.04 is right here, and then all the way down to the bottom row. And I think it says 1.751 down there. I'm trying to erase this other thing. But it won't, so I don't know what that's all about. That's fine. You should see a 1.751 there. And again, that was a 4% alpha and one tail. I'll draw a little picture of that. So 1.751 standard errors is considered statistically significant. Just as a reminder, we got for our test statistic, we got 2.22 standard errors. So I think, yes, we can call that significant. It does go out into the tail. So I'll put a mark down for this. Okay, and because it makes it out past the required number of standard errors, we would consider it significant. I don't know how significant. I need a p-value for that. Okay, any questions about anything yet? This is weird stuff, so please don't feel shy about asking questions. Okay, now the p-value measures how significant it is, sort of on that sliding scale. So there's a picture here again for the right tail test. You have the alternative hypothesis saying mu is greater than something. Left tail test has H1 saying mu less than a value. And of course the two tail test, H1 says mu is not equal to a value. Okay. So I think we're doing a right tail test because we're saying mu is bigger than 100. So let me go ahead and draw a right-tailed distribution. And on this one, you label the test statistic, which is the 2.22 z-score. So that's the area you want to find. Okay, any questions about that? Table A1 has areas under the normal distribution. So you just find your z-score, which is 2.22. This way. Let me pop over to that real quick. Table A1. And so hopefully you're seeing what I see here, which is 0.9868. Okay, any questions? That's not the p-value. This is giving the area to the left always. Don't forget, only gives areas to the left. This is a right tail test. So we need to doctor that a little bit. Okay, so 9868 is what it says. That's the area to the left. We need the area to the right. So we have to do 1 minus 0.9868. Can we do that yet? Oh, 0132, thank you. 0.0132. That's our p-value. And I'm just going to move things around a bit so to kind of get rid of some of this clutter. Or at least to make it a little more clear. I feel like I need to draw a line to separate the diagram and what I drew for that. All right, so that's a small p-value, it's less than 5%. I don't remember what the alpha value was, so I'm going back up. Yeah, it was 4%, okay, 0.04 for alpha. And that's the critical part. So the p-value, 0.0132 is less than 0.04, which is alpha. Now this is, again, I have this sentence written again and again throughout all these documents. make a conclusion. If the p-value is less than the level of significance, yada, 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 we reject the null hypothesis in favor of the alternative. Otherwise, we fail to reject the null hypothesis and don't support the alternative. So that's a wordy, sort of a wordy way to conclude, but maybe I would be willing to copy this down that we wrote on the last lesson. So, because it's always this idea. Small p-value causes rejection of the null hypothesis. So I'll paste that in, and that will be the rule for the rest of the semester. And it's just a kind of a brief way of explaining what I explained in this paragraph here. Okay, so p-value is less than or equal to alpha, so we reject the null hypothesis. Null hypothesis says that the mean is 100. We're not going with that. But we are supporting the alternative, H1, which said that the mean is greater than 100. I don't know what, I'm not saying what it is. I do have 106 from a sample, but that was only like 35 students. And there's a lot more statistics students out there. So it's silly to act like you know what the mean is. But we have evidence that it's more than 100. And so we can speak with a certain amount of confidence on that. So we'll say the data are what tell us this. They support the claim that the mean IQ for stat students is greater than 100. Okay? Easy. Just going to pause and wait for questions. Okay, no questions. So we're going to go to the next one. It's just another example, basically the same thing. It says from 75 random patients, a 200 milligram tablet of acetaminophen is given, and the body temperature is measured after 2 hours. Their mean temperature is 97.8. Assuming the population standard deviation is 3.5 degrees Fahrenheit, test a claim at 3% significance that the mean temperature is below 98.6 degrees Fahrenheit 2 hours after taking acetaminophen. And that's just Tylenol. We know Tylenol is pretty good at lowering body temperature. Okay, it's one of the good ones. So let's see how this goes. So sample data, we're basically a sample size of 75. We got a 200 milligram tablet of acetaminophen. Again, that's Tylenol. Body temperature is measured after 2 hours. The mean, here we go, this is from a sample. So the mean temperature is 97.8. Assuming a population standard deviation, okay, that's sigma for population standard deviation, is 3.5. Test the claim at 3% significance, that's our alpha, 0.03. That the mean temperature is below 98.6. That's an alternative hypothesis, mean below 98.6. People have used to assume that the average body temperature is 98.6. I think it's a little less than that. I think I've read that the mean body temperature has gone down over time too, just a little bit, just a tiny amount. I can't remember why they were saying that. Okay, but regardless, they're saying the mean is less than 98.6. So let's take our alternative hypothesis and say the mean, which is mu, is less than what they're saying here, 98.6. Okay. So generally, again, I always do the alternative first, because that's usually what they claim, and then you go in and say, all right, well, they're saying it's greater, but for the null hypothesis, we have to assume it's equal. That's what we're comparing to. And we use it for our z-score that we compute next. Oh, I didn't do my check. Where's my check? What should I write for my check on this one? Anybody remember? N has to be how big? Daggone it. Good try. Then now the 10, yeah, the 10 is for proportions. So we're doing means, and means have different rules. So here, when you do means, the sample size needs to be bigger than 30. So sorry, it's sort of a trick question. Okay, so I hope I wrote that before. Let me double check. Check either n is bigger than 30 or the population is normal. We're good to go. Okay, test statistic. This is z test statistic. Z is x bar minus mu over the population standard deviation, which we're assuming is known, divided by the square root of the sample size. So x bar was 97.8. The mean is assumed to be 98.6. That's what people have always said. And then over sigma, 3.5 divided by the square root of n, which is 75. Okay, so see if you can get what I get. Be negative this time. It's the left tail test. Type it in when you get it. 2 places after the decimal. Yeah, thank you. Negative 1.98. So that's almost 2 standard deviations below. Seems significant, but I'm not ready to decide that until I get my critical value. So on the bottom row of table A2, that's the one that asks for degrees of freedom. That's for t-tests. Z distributions are just under large here, and in parentheses we write Z. Okay. Our alpha was 0.03, I think. Yeah. 0.03, and this is again a one-tail test. I should have denoted this. On H1, mu is pointing left. Okay, so that makes it a left tail test. Which main thing is it's not a two-tail test. So we'll just write one tail as opposed to two tail. Make sure you look up under one tail. Okay. And I'll pull this up real quick. It's again table A2 for the critical values. And one tail 0.03, is it here? Yeah, it is, right in the middle there. There's a 0.03 for one tail, and then all the way down. Make sure you got that. One tail, 0.03, looks like 1.88. That's the number of standard errors for statistical significance. Any questions? Okay, so it says 1.881 standard errors. Now remember, this is a left tail test, so what that means is standard errors below the assumed mean, which makes this a negative z-score, negative 1.881, because it's just a left tail test. You just have to make this negative. I get it. Okay, so, and then don't forget our z-score, the test statistic, is coming out to the left of this. So the negative 1.881 is a critical value, but the test statistic was negative 1.98. And because that's in the tail, we consider that significant. Statistically significant. Okay, any questions about that part? Okay. Then comes the p-value, table A1 still. So, or table A1, I should say. So here we go. This is our test statistic now. Find how probable it is to get something this small. We got negative 1.98. So we have to go down for z, we go down to negative 1.9. And then over to 0.08 to get that probability. Remember, this table gives areas to the left of your z-score. That's what we want, actually, because this is a left tail test. Okay. So, the area to the tail to the left is what gives the p-value. Okay, so let me jump over to table A1. This is a negative z-score, so here's negative 1.98. This is what I see, 0.0239. Any questions about that? This again is a left tail test. This table gives areas to the left, so that's a good number right there. That's our p-value. Okay, any questions? All right, so 0.0239. That's our p-value. Any questions? Okay, and then you can make your conclusion. Same as before. So our p-val is 0.0239. I'd consider that statistically significant, and it's less than 0.03, which is our alpha. level of significance given the first step. And I wonder if I still can paste that last thing I did. Yep. So those are the criteria for making a decision. Okay, if p-value is less than alpha, you reject the null hypothesis, support the alternative. So here we're rejecting the claim that the mean body temperature is 98.6 when you're on Tylenol. In fact, we're going to support the claim, the alternative, that the mean is less than 98.6. So the body temperature is now brought lower when you put someone on Tylenol, and the data are in support of that. So I'm going to somehow squeeze all that in. There it goes. The data support the claim. That the mean body temperature is less than 98.6 degrees Fahrenheit 2 hours after taking Tylenol, I think, which is called oh Lord, what's it called? Acetaminophen. Acetaminophen. Yeesh. There you go. Okay, any questions? So it's the same. The next two problems are the same as well. But we go with sigma unknown. And we talked about this. I'll mention again in a second. Just waiting for any questions at all.